Okay. And Kate, can we
Hello,
hear you?
everyone.
Okay. I think we can hear you.
You can hear me, you can see me. Good.
We can hear you, we can see you, we can see your slides. That's great. Okay. So, so Kate Verbitskaia. Okay, how do you pronounce your last name, Kate?
It's Kate Verbitskaia.
Okay. And Kate's going to be talking about semi-automated direction-driven functional conversion. This is work out of JetBrains research, and I'm looking forward to seeing what Kate has to present. And also, once again, I'll mention that Kate has been organizing this extremely interesting monthly miniKanren research seminar online. So if that's something you'd be interested in, please let us know, and we're always looking for speakers for that. Okay, Kate, please take it away.
Okay, thank you for the introduction. Let me start. I will be starting this talk, and then Igor will join me for the second half of the talk. So let's start. And my cat is always in my face when I start doing any presentation, so sorry for that. So we all love relational programming because it allows us to express non-determinism. It also guarantees us completeness of search. But what's more important for me, at least, it's that one relation allows us to solve many problems. This is used in this idea of using relational interpreters for search problems. Here we use usually you either already have a relational interpreter which you run then to solve a greater problem, or you can even translate a function. So you just write a interpreter in your favorite functional language, translate it into a miniKanren relation, and then you run it in some direction to solve a more complicated problem, such as search or generation or whatever. And here this approach is very nice, but of course it struggles with performance. And the performance is something which we try to improve with our in some of our attempts to do some stuff statically. So when we are talking about directions, we don't usually only limit ourselves with a forward and the backward direction. We always have more. We can actually express almost an infinite number of directions, but we will only talk about the principal directions here when each of the arguments of a relation can be either completely known or input, or it can be completely unknown output, such as a fresh variable. We don't allow any partially known terms, such as this constructor with unknown head. This is not allowed. Otherwise, it's all good. So, for example, for the addition relation, which relates to numbers with its sum, we have 8 possible principal directions, some of which have names, some of which don't. So for example, forward direction can be called addition. The backward direction can be called decomposition. We can also have subtraction when we run it with unknown either x or y. And we have some other notable directions such as predicates and generators. Predicates, they check that 3 values are indeed in this relation, and generators enumerate every possible triple of numbers which are in this relation. Each of these directions basically works as a function. Well, kind of. Some of these directions are indeed functions. They can only produce at most one possible answer given the inputs, such as like addition and subtraction, of course, are functions. They always give us only one possible result. Predicates also can be viewed as a function which produce some kind of a like Boolean or something like that. But other directions are often relations. And what I mean by relation is that they produce multiple results, multiple answers. They are non-deterministic. But of course, as you probably know, you can express non-determinism in a functional programming language as using some kind of a monad for that, or some kind of other technique. For example, like in Haskell, it's very common to use lists to express non-determinism, and we will use streams to express that non-determinism. So basically, what I'm trying to say is that each direction is a function, and it's it would have been really nice to be able to run these functions on their own. Unfortunately, when you run miniKanren in any direction, it always comes with an overhead, which we already discussed at length, right? So we have unifications, which are costly, occurs checks, which are even more costly. We have scheduling complexity, which is another big thing which impacts the efficiency. And what we would like to do to get rid of as much overhead as possible. So one person during the talk, which Will gave earlier today, asked how maybe it's possible to combine functions and relational programming language and use relational computations only when it's needed. And this is one of the things which we try to achieve using our functional conversion. So a functional conversion is a process which, given a relation with a principal direction, constructs a functional program that generates the same answers as miniKanren would. And here we want to preserve the completeness of the search, otherwise it wouldn't be like miniKanren in the spirit of miniKanren. And here we always assume that both inputs and outputs are ground. So why it's important, why we can expect outputs to be ground, it's because we usually, when we interact with miniKanren from the functional world, we don't even know how to deal with fresh variables, right? It's something which is foreign to the functional program. So in doing our functional conversion, we want to produce ground results for each output which the user expects from us. And let me start by introducing several examples which demonstrate functional conversion, which illustrated, and then I will talk about how it's done, and Igor will talk also about how it's done. So here at this slide we have a addition relation implementation. It works over piano numbers representation. It examines the value of x, and we know that if x is 0, then the sum of x and y is z, and if x is not 0, then we can do the recursive call, and then we just add a successor to the z to get the result out of that. This is one of the implementation of this addition relation. Of course, it can be different. So let's consider the forward direction of this relation, this function which sums two numbers together. We usually use this notation of using i's in place of ground variables known as inputs, and o's for the output variables. So add IIO works as a forward direction for the add-do relation. Here we know x and y, and if we know x, we know that these two conditions, these conti branches, they are disjunct by x. So it's based on the value of x, either the first conti branch or the second conti branch can hold, otherwise, and the other would fail. So it's natural to translate that into a pattern match. So we do the pattern match on x, and then we consider the rest of the conjuncts within these conti branches. In the first conti branch, we see that the result z is the same as y, so we can return y as a result in this pattern match branch. If x is a positive number, then we know that after this pattern match, we know the value of x prime, x1. So if you know x1 and y, we see that this add-do relation works in the forward direction. We can call it to get the number, the value for z1, and that value of z1 with another successor constructor will produce us the result for the whole call. So we do the call, the corresponding function for this direction with x1 and y, and then we add the successor on top of that to get the result. It's very easy when we talk about forward directions, but of course it's not that simple. So for example, if we consider the backward direction, when we only know the last argument, we cannot say that these two Kandi branches are disjunct based on z, because z is indeed a positive number in the second branch, but we don't know anything in the first branch. So in this particular case, we need to produce answers for both of the branches and then combine them together. And as I already said, we can express non-determinism differently. And the most natural solution which we can when we are working on miniKanren', on relational programming, is using streams, which is one of the basic structure which which holds all the substitutions, which holds all of the answers. And stream is nice because its concatenation, it's a monad which has this bind operator, which allows us to express conjunction, and it also has m+ operator. M+ concatenates streams, and with binds, it makes sure that streams are interleaved. So we never have this problem which prologues usually have, that you start to explore the search space somehow wrongly, and then you never get any new results. So to make sure that we still have completeness of search, we use streams to represent answers from each of the Kandi branches. So let's consider these branches. The first branch generates us a singleton stream of answers. So it's only gives us one possible result when x is 0 and y has the same value as z. So to construct a singleton stream, we use return, which creates this stream of one particular tuple. And the second Kandi branch, it starts as a pattern match because we know that z is always a positive number. So if z is 0, we return an empty stream. This is like a failure. It can never happen that we got in this second Kandi branch and z is 0. But if z is not 0, then we proceed to examining other conjuncts, and we can run the addition in the corresponding direction. We get the x1 and 0 and y results, and then use the constructor to construct the resulting tuple here. And I've been using Haskell's do notation here, which is like a syntactic sugar for binds. Binds are one of the basic stream operations, and returns just create singleton streams, and empty streams just express the failure here. So I hope this is readable, this Haskell notation. If not, just ask me a question. And one other notable thing here is that I reordered conjuncts while I was doing this functional conversion. I don't know if you've noticed, but I did. So in this conjunction, I first used the last unification, then I used the call, and then I used the first conjunct to get my result. And this order of conjuncts is something which we have to figure out during the conversion, and I'll try to talk about it a little bit more later. One other complication which can arise is that in some directions, we are left with values with variables which are unified with no value. They are not unified with any value. For example, when we only know the first argument for the addition, the first disjunct here, the first Kandi branch, it unifies y with z, but we don't know either the value of y or the value of z. In this particular case, miniKanren would just return a fresh logical variable, but we decided that it's not okay to do so, so we use generators. A generator is a stream of all possible values which a variable can take. And generators is something which we leave to users to provide, but the only thing which matters is that it's supposed to be a stream, because otherwise we would not be possible to do the completeness of search, to guarantee the completeness of search again. And everything else is in the translation of this particular direction is mostly the same as the previous two examples. So, all right. Let me proceed to doing the conversion scheme, to explaining the conversion scheme itself. So we have 3 steps: normalization, which is like a helper step, mode analysis, and the functional conversion. So normalization is just a way to make a miniKanren goal to be a little bit less complicated for the steps ahead. We limit our terms to be either a variable or a constructor applied to a list of distinct variables. We disallow constructors within constructors, we disallow repeating variables here. And it is a simple syntactic transformation to get rid of these kind of terms. They are translated into a conjunction of corresponding unifications of corresponding variables. When it comes to goals, we have a little bit more restrictions. So first of all, we only allow disjunctions on the top level. So we can see that we can think of it as a conD on top. Every relation starts with a conD. And then we have conD branches, which are made out of non-empty conjunctions. And each conjunct is either a flat unification or flat curl. Flat here means that we have all the variables distinct, we only use variables, and unification unifies a variable with a flat term. So we only have constructors on the right-hand side of the unification. After we've done all of this normalization, then comes the hard part of actually doing the conversion. We start by this mode analysis. The prime goal of mode analysis is to determine an order of conjunctions, the order of conjuncts, base goals within conjunction, in such a way that it makes sense. And what makes sense is a complicated thing here. Let me just walk you through a couple of definitions first. So each variable each term can be either ground or free. Ground term does not contain any fresh variables, any logic variables. It can only be a term such as this example here, a list of 2 numbers, 0 and 1, and we cannot have any logic variables inside of it. Free variable does not have is a fresh variable, doesn't have any constructors in it. And once something becomes a ground term, it always stays ground in the later conjuncts. And this is the idea which helps us to order conjuncts more or less in such a way that they make sense. So this groundness or freeness, it's called in the instantiation of a variable. Of course, there are more complicated instantiations, but we only limit ourselves with these 2 for now. Mode of a variable explained is a mapping between its instantiation before and after some base goal has been executed. So we have 2 modes, I and O, which we've already seen. And I means that something has been ground before and it's still ground now. Mode O means that something has been free. We had no idea what the value of that variable is, and then it became ground. And this idea, of course, is not new. It's used extensively in the functional logic community. Mercury, for example, uses more complicated modes. But our job was to limit ourselves as much as possible to get as best result as possible through our conversion. Because I still believe that we don't really need to write a separate compilator or translator for miniKanren, we have to try to do it in the embedded way. And to do so, we need to make it simpler. So the goal of mode inference or mode analysis is to assign modes to every variable and make sure that they are consistent. So no ground variable becomes free. We have these 4 possible ways the unification can be moded. So we can assignments where we have one output variable at one of the sides of the unification, and the other side is input or completely known. It can be seen as a regular assignment in a regular programming language. There are these guards where we have ground terms on both sides of unification. In this case, it works just like an equality check. The more complicated ones are matches and generators. Matches is when we know a variable and we try to decompose it into a set of into a term. So on the right-hand side, we can have a term which contains ground and free variables. So at least one free variable is at the right-hand side. And generators are the worst out of these moded unification types, where we have output variable on the left-hand side and a term which contains output variables on the right-hand side. So let's talk about how moded inference work. We start by initialization. Initialization just puts input mode, associates it with input variables, output mode with output variables, and this question mark mode with all other variables. The question mark mode maps a free instantiation into an unknown instantiation, which is supposed to become ground after we have done our inference. To do the mode inference, we start by examining a disjunction. To do so, we examine each of the candy branches separately, because they never interact by variables, so it's safe to do them each on its own. When we have a unification, we just propagate the groundless information. So we knew that, for example, here we knew that X is input on the left-hand side of the unification, and we have the question mark mode on the right-hand side, which means that X1 has been free before this unification, but we know that it can become ground after it's done, because we know the value for X. So this unification after mode inference becomes this unification, where we have input on the left-hand side and the output on the right-hand side. The same goes for other combinations of different variables. The most complicated part of mode inference is treating of conjunction. Here, as I've already said, we have to reorder conjuncts in such a way that it still makes sense, and we also try to not introduce any more inefficiency in the system. We try to instead reduce it. So each conjunct can be seen as one of these 6 types. One of which is guards. Guards is the safest conjunct to execute, because it can only trim our search space. It can either fail or succeed, and when it succeeds, it doesn't introduce any new variables, it doesn't do anything. It just succeeds with the check mark. It doesn't introduce any variables into our search space. So whenever we see a guard inside of conjunction, we can pop it right away, put it the first in our conversion, and proceed with other conjunctions. Then the safest 2 out of the rest types are assignments and matches. Then they can also fail during. They can fail and trim the search space, but they don't really make a lot of computations when they are processed, right? Assignments don't even introduce variables. Matches introduce variables, but they don't do any associated evaluation during that. The 3 remaining types of conjuncts are worse. And the worst of them is the call with all three arguments. It is the worst possible way to run a relation, miniKanren relation, because it produces all possible arguments, all possible answers to it. So we try to push it as far as possible in the hopes that previous conjuncts would make some of the arguments ground and then trim the search space. The second worst is unification generators. They always produce, almost always they produce infinite streams, so it's good to push them down. And calls with some ground arguments, they can be either deterministic or not, and we cannot even tell from the shape of them. So, but we know that they are better than calls with all three arguments, right? So we pick those conjunctions after matches, but before generators. So basically, mode inference of a conjunction is picking a conjunct according to this priority. And let me demonstrate. So here we see the conjunct of our addition relation. We don't have any guards here because we don't have any unification calls with all the input variables, but we have a pattern match. The second conjunct here is a pattern match. So we pop it up. We learn the value of x1 by doing unification. Yes, it becomes ground, and it stays ground in all the subsequent conjuncts. So we can see that add-do applied to x1 and y now works in the same direction as we processing now. We're processing now. So it's always in the forward direction. We can run it because it's not a generator, right? We can get the value for z1, which becomes output here and input here. And the last conjunct is already moded. We don't really need to do anything, but it's, you can see, a safe unification because it does not have any free, so it doesn't have free variables on both sides of the unification. So this is how it's done, the mode inference. And one thing to notice is that one limitation it has, it still have no idea how to order calls which have some ground and some non-ground variables. So for example, if you have the multiplication relation, which uses addition to add, what is it, x minus 1 multiplied by y to y, there are two possible orders we can put the addition and multiplication relation calls. So if we try to push the recursive call to mult as far as possible, we get a very, very slow relation because this addition, it generates an infinite stream, which is then sifted through by this multiplication, which is already a costly operation. So this is a case of generate and test behavior, which we want to avoid as much as possible. And this particular order would work much better if we first put the multiplication and only then addition. It's currently not, we don't have any good way to order these conjunctions, but we think we had some heuristics which helped. So, okay, let me pass to Igor. Igor?
Yes, hello. My name is Igor Engel, and I was working on the translation parts from model miniKanren to functional languages. To facilitate this conversion, we introduce an intermediate language that is a middle ground between functional constructs and miniKanren. It has a few operations, a few of which correspond, four of which correspond to various model unifications. So that's return for assignment, match bind and match generator and guard for other unifications. It has a bind operation which corresponds to conjunction strings, and a sum which is interleaving of strings. We treat generators as their own special entity, and we pass them in calls. Next slide. So here's the high-level review of the translation. We translate a disjunction to sum to interleave the strings of various branches. We translate conjunction to bind also allowing next conjuncts to use variables produced in the previous ones. Relational calls are translated to functional calls and passing of generators, and the indication is depending on mode into one special operations. And the main problem during this conversion is generators. In non-type miniKanren, we cannot create a generator automatically, or we can, but the only one is possible to create is to generate all possible terms, even of mixed types. So, for example, a number successor of a list, which is a nonsense term, but will clog up the string. So instead, we ask the user to provide the generators to function as additional arguments, and we utilize them to mimic type system. We require a generator for every free variable in the right-hand side of unification generators, and also those requirements are transient. So here is an example of multiplication relation that doesn't require a generator by itself, but it needs to pass a generator to addition relation also. In the type version of miniKanren, it should be possible to generate those generators to derive those generators automatically from types that will produce all values of a given type. After we convert models miniKanren into intermediate language, we can convert intermediate language to some functional languages such as Haskell and Camel. We've written both converters. For Haskell, we use employed Haskell to generate code and stream monad and notation process it. And with OCaml, we use handcrafted printer, OCaml version of stream monad and let's start syntax for its use. And we also need to have some special care because OCaml is an Igor language by default, and miniKanren needs a lot of laziness to work. So after we translated our miniKanren relations, we can evaluate them and see whether we achieved any sort of speedup. We have two evaluation targets, logic formulas generation. So given an interpreter or logic formulas on a given state, we want to produce some formulas, and a multiplication relations run in various directions. For logic formula generation on a free variable state, providing formulas that evaluate to true, we can see roughly a twofold speedup. It's one of the less impressive examples here, but we can also consider further optimizations for it, which we'll discuss later. For multiplication, we can see a 200-fold speedup, for example, here in forward direction. And in other direction, we also see something along this magnitude even better, backwards direction. And here's an example presented by Kate earlier when we have two possible functional translations, one of which is very slow, much slower than relational version. That's the one that which utilizes generate and test behavior. But if we use faster version, we still get a tenfold increase in this direction. And one of the specifications which is not currently implemented but is on our radar is monad substitution. So when a relation is non-deterministic, we need to utilize streams for it. But for a semi-deterministic relation that produces at most one answer, but may sometimes fail, we can substitute the monad for maybe. And this doesn't require any change to the code produced. So our code is already compatible with this optimization. We just need to figure out when it can be implemented and change the type of the function. This optimization gives another tenfold increase on top of our previous increase in performance of the relational functions. And if we can prove a relation is fully deterministic, so it produces exactly one answer, we can also try to have a non-bonus version, which should be even faster. And we are currently investigating using various determinations check to figure out when it's possible to use this optimization. And another optimization that should be beneficial with combined with functional conversion is partial deduction, where if we have some fixed argument for a relation, we can propagate it and eliminate some branches of a relation that should significantly speed up the conversion program. So in conclusion, we presented a functional conversion scheme that can speed up relational progress by orders of magnitude. We implemented the conversion scheme in Haskell, and we have a full translator that can take a miniKanren program and output a Haskell raw command code. And we have some way to order conjunct that works most of the time, but first work is needed on this. We currently are working on determinism checks for seeing where optimizations can be used, integration with partial deduction algorithms to further optimize the code, and integration into framework of using relational interpreters for solving for synthesizing programs. Thank you. We are ready for questions.
Thank you very much. Let's thanks the speakers for a very interesting talk. Okay, I have a lot of questions, but does anyone in the audience have questions? No. Okay.
Hi, Walter Schulze, Go miniKanren. I was wondering, you're generating functions from a logical proposition, essentially. Have you thought about also generating a proof to show that these two are equivalent?
I don't think we've thought of it because it has not been our task. Do you think it's going to be easy or beneficial or?
I think a lot of times, like in Coq or Lean, you write a logical proposition to describe your function, and then you write like the optimal function and you prove that they're equivalent. So this would be, the function you're generating might be something in the middle where it's not necessarily the optimal function, but at least a function. And like even having the proof that this function is equivalent to the logical proposition is a big step that might help prove the optimal version. It would save a lot of time. Like proving is very expensive. So
well, that's basically amounts to formal verification of our translator, right?
Yes,
So
yes, it doesn't, like we don't introduce anything which can break currently the function. It's, I mean, we can prove that our converter works. That's should be enough.
Yeah. So it should be possible to provide a formal verification that a converter is accurate. We haven't yet done so, but it's possible future work.
cool, thank you.
Thank you.
Thank you. That'd be interesting potential future work. Any other questions? Okay. Oh, we got another question. All right.
I was also wondering, have you looked at the rewrite rules that Verse has for its logical expressions? Like maybe there's some cross collaboration work there possible.
Yes, the verse is something which I really want to explore more. Currently, like by the time we've come up with this project, verse hadn't even existed back then. But we had the Mercury and Kari and other examples of functional logic programming, which we explored. And this particular work is heavily influenced by Mercury, the way Mercury works. But neither of these tools guarantee us the completeness of search, unfortunately. And I also believe that by simplifying as much as possible and employing, instead of employing like something like partial deduction or supercompilation on top of that functional conversion, which we're already doing, it should be enough and it should be beneficial already. It's a little bit different approach, I would say.
Yeah, I really appreciate the way it's very simplified. Like, yeah, well done, great talk.
Thank you.
Thank you. Okay. Any other questions before I ask questions? Okay. I too, by the way, am very interested in verse and verse calculus and how that might tie into miniKanren. Now, speaking of functional logic programming, I think what you've implemented, as far as I can understand, isn't really functional logic programming like you get in something like Curry. It's really a more efficient way to try to do relational programming, right? So like the Kent Divig says, optimization is the art of cheating without getting caught. So you're cheating without getting caught. Just you're noticing that certain relational patterns you can just do as functions. But that's different than having a functional logic language where you have lambda in the language, for example, or where you can do traditional functional programming. Do you think that it would make sense to extend this work or to play around with this work where you could do sort of a functional logic version of Kanren or Okanren or something like that, where you actually somehow combine the functional programming, relational programming more deeply, where you get something more like Curry or Verse?
I would say that we are already halfway through there, because currently we like what we currently are doing is getting rid of all miniKanren. We don't need to do that actually. We can do that only for deterministic relations, or we can directions, or we can do like for stuff which we know is finite. For example, like and or whatever works, which works on the Boolean or other finite domain terms. So if we have these ones, we can translate it into a host language and then interact by miniKanren with this host language. Like, because we already have this miniKanren embedded into a host language, we already have some kind of functional logic programming, right? So this is how I view it.
All right. Although right now you still can't do things like use lambda and do higher order programming, I don't think.
No, higher order is, I think it's out of the question right now. It's too much.
I think that's the tricky part, is really using lambda and higher order things. So I think that's
do we need it in miniKanren?
Well, that's a good question. I don't know. Right now we kind of encode lambda through writing an interpreter for a language that has lambda, and then kind of that's sort of a cheat to kind of get around it. But it is an interesting question: do we really need lambda? You could argue that in standard miniKanren, we can't do things like implement capture avoiding substitution nicely. So unless we have nominal logic or we have something higher order where we can do higher order abstract syntax, we can't even implement capture avoiding substitution properly. We can't do gensim relationally and things like that. So those are areas where maybe we would benefit from having something more higher order, but I'm not sure.
Yeah, but I mean, given how it's hard to optimize miniKanren as it is.
That's fair enough. Speaking of which, one thing Dmitry mentioned in the last talk was that it would be great to have sort of this, I don't know, macro miniKanren. It's a big miniKanren that has all of the optimizations and all of the special, versions. Right now we have a whole bunch of different implementations of miniKanren in different host languages with different logics and different optimizations and different constraints. And you have a very nice set of optimizations here. I think part of the problem is we haven't really figured out how to have a single system that combines all of these approaches in one system. So have you given any thought about how you might, have a system that combines all of the things we've learned about how to make miniKanren and relational interpreters and all that fast in a single system? You're also doing partial deduction. That's one piece of it, but there are a whole bunch of other things that we've figured out over the years might make programs faster. But it seems tricky, or maybe it's more of a software engineering issue. But we haven't successfully combined them all in one implementation. Have you thought about that?
Well, I'm currently trying to think how to combine partial deduction with functional conversion and make it all live as an embedded language. And it feels like I have my plate full with that.
Okay.
But
fair enough.
I do believe that this is a beneficial approach to combine different optimization. I would definitely want to explore it more. And Igor is very talented software engineer, so we can, I think, tap into it.
Great. Was there a big difference between the Haskell implementation and the OCaml implementation? Like, did one feel much more natural than the other when you're implementing this?
Well, Haskell implementation was much more natural because we were writing the translator in Haskell. It was everything but for OCaml.
Well, I mean, this functional conversion into the target language is the very last step, and I think that I whipped the pretty printer for OCaml in maybe a day after everything has been done by Igor with that intermediate language. So I don't really think that it's hard to include any other target languages. But it was pointless to use our Haskell implementation and compare running time of miniKanren because my Haskell interpreter for miniKanren is even worse than anything else. It's just a basic microKanren implementation. So we decided to put it into a OCaml to be able to compare it with the OCanren. So all of this evaluation was done in OCanren. And it seems to give us some kind of good improvement.
And do you think your approach could be applied to scheme or racket implementations in miniKanren, or is there something about the types that you need?
Currently, we don't even use anything about types. We only need streams with their binds and plus operations, and nothing more.
Okay, so this should be applicable to scheme as well.
Yes, because generators are up to the user. You can write whatever generator you want, and it's the only place where you actually need types.
Okay, great. That's definitely something I would like to explore. Well, thank you very much. And let's thank the speakers one more time.
Thank you for the discussion. It was very nice.
And I'll add the plug one more time that Kate runs this monthly miniKanren online seminar, research seminar. So if you're interested in that, let me know or let Kate know, and hopefully you can share your research.